This is the nonparametric procedures presentation, part 1, EACS 6023, Applied Quantitative Research Methods in Educational Administration, University of Oklahoma. Chi-square is the primary nonparametric procedure, so we'll focus most of the presentation on the chi-square procedure because it's the one that's most commonly used. However, there are other non-parametric procedures that are available to use too, but it's by far the most common and probably the most simple. So even though the title of the unit is non-parametric procedures, the title of the presentation is chi-square because chi-square will be used as the primary exemplar of non-parametric procedures used in quantitative research. And a definition of non-parametric procedure, this is from slide 2 of your presentation, or PowerPoint presentation. Chi-square is a popular non-parametric procedure, and non-parametric procedures are the same one to another in that these assume no underlying distribution of data. In other words, we're really not measuring anything. The difference between a non-parametric procedure and a parametric procedure is that with a non-parametric procedure, we're not measuring, we're just counting. With a parametric procedure, there's some systematic way of measuring things and including them into the analysis. Non-parametric is really all about frequencies then. So it's not considered as strong as a parametric procedure, not as precise as a parametric procedure, but sometimes non-parametric data are what we're working with depending on the type of study that we're doing, and we need to use a non-parametric procedure. And typically if we use a non-parametric procedure, chi-square is the procedure of choice. And chi-square is really kind of a nice little procedure for looking at different frequencies and distributions, and sometimes it's very germane to a research question or research issue that you might be asking. So it's certainly a good analysis, as are other non-parametric procedures, but again, it's not considered as precise as something like a regression where you can really measure fine distinctions among data. In effect, with chi-square, we're using categorical data and just looking at frequencies within categories. So all categories in a non-parametric procedure are nominal or categorical variables. That's really how it's defined, in other words. And you're not looking at, say, how a treatment group and a control group compare on some sort of outcome measures and then doing some statistical comparison on it like you would with a t-test or with some sort of analysis of variance. Or you're not looking at the relationship between one or more variables with some predicted outcome like you would be with a correlation or regression analysis. Instead, you're looking at different categories to see how the distribution of subjects within that categories measures up against each other. So again, there are times when using a chi-square or another non-parametric procedure is fully germane to the research context. So it's an analysis of frequencies. This is page 3 of your PowerPoint presentation. Chi-square and other non-parametrics are an analysis of frequencies, and we'll talk a little bit about two major types of chi-squares, and that's goodness of fit and contingency chi-squares. And the statistic for the chi-square procedure itself is the Greek letter chi. It looks like an X, but it's actually the Greek letter. We call it chi. Actually, the Greeks pronounced it chi, but we kind of anglicized it and made it chi. And of course, it's squared, so it's a chi-square statistic. And you'll see when we do the computation, there's actually squaring is part of the formula, so that's why it's a chi-square. And it's a test statistic, just like an F statistic with an analysis of variance, just like a T statistic with a t-test, or like the regression coefficient, which we denote as B in a regression analysis. We have a test statistic that is actually calculated, and if that test statistic is big enough and it's bigger than a critical value, then we say there's a statistically significant frequency distribution in the population, and we'll kind of talk about that in a little bit. There was actually a test statistic being used in a chi-square analysis. And we intimated just a few seconds ago that there are two primary categories of the chi-square analysis. First is the goodness of fit model, by far the simplest of the two models. And the second is the one that's more of a contingency analysis. And the simplest of two, chi-square as a procedure is really not a very complicated procedure. It's fairly simple. It's simple to interpret and also simple to calculate. Actually, SPSS, though, surprisingly, when you look at the SPSS demonstration for this unit, SPSS, I've never thought the chi-square analysis was really that great in SPSS, but there is a certain procedure for doing the SPSS analysis that we'll do in the demonstration, and once you kind of get the hang of it, it's not that difficult. But it's pretty easy to interpret the chi-square. So those are the two primary types of analysis, goodness of fit and contingency, and we'll talk about both of those here in a few seconds. First of all, the goodness of fit. This is slide number 4 in your presentation. The goodness of fit type of analysis is in many ways akin to the one sample t-test. Instead of comparing two samples against each other or two groups against each other, what you're doing is you're taking a single sample and comparing it against some sort of criterion. Only instead of measuring this sample, we're actually counting the numbers of subjects within levels of the category. So it's one independent variable and one criterion. Sometimes that criterion is one of a random distribution of data points. Sometimes it's something else. Is the pattern of frequencies, the question that's being asked with the goodness of fit analysis is the pattern of frequencies random across the categories, or does it fit some sort of predetermined pattern? Let's say you have a population pattern that looks like X, Y, and Z, and you want to draw a sample in a different kind of context to see if the pattern in your specific context fits a broader context. Does it fit X, Y, and Z in the broader context? It doesn't have to be perfectly random. It's just you're testing with a chi-square goodness of fit analysis. You're testing to see if the frequencies fall in some sort of predetermined or pre-understood pattern of distributions. And hopefully with an example we can kind of clarify what that means. So in effect, and this is still slide number 4 of your presentation, what we're testing for if we do a statistical analysis, an inferential a statistical test, we're testing to see if the observed frequencies equal the expected frequencies. So as you can see, it's rather a simple type of model. It's just, this is kind of what we expect in the population in terms of frequencies within levels of the categorical variable, and we're collecting data in a sample to see if our actual observed frequencies within levels of the category are equivalent to what we expect these frequencies to be, whether they be a random set of frequencies or some sort of predetermined set of frequencies that we know to exist and we're simply testing. So it's a fairly simple type of analysis. And again, this is the goodness of fit analysis, subcategorized under the chi-square analysis, which is a further subcategory of nonparametric tests. Again, nonparametric set test assuming no pattern or distribution of data, is just looking simply at counting subjects within categories. So the null hypothesis would ask, are the observed frequencies equal to the expected frequencies? And of course, the alternative for the research hypothesis would be, are these observed frequencies not equivalent to the expected frequencies? The calculation of the chi-square, again, not a really complex formula. Chi-square is our test statistic, so it's on the left side of the equation, and it's equal to the sums of the squares of the observed frequencies minus the anticipated of the expected frequencies, all of that divided by the expected frequencies. So that's the calculation of the chi-square goodness of fit model. It's really not that difficult to do. You kind of start with the part you start with the numerator, start with the part in the parentheses. You take each observed value, subtract off the expected value, and square it. And then you have a square for each observed value. Then you sum down the number of observed values, add all of those up as a sum, and divide it by the expected value total. So that's the calculation. the degrees of freedom for the chi-square is equal to the number of categories minus 1. And then one looks up the critical values on page 364 of the Salkind text. And that provides a series of critical values under different type 1 error rates and for different levels of degrees of freedom. And that's actually the critical values, whether it's the contingency analysis or the goodness of fit analysis. And also you can also download chi-square critical value tables from the internet as well. The Salkind text has one, but you can get others from other sources as well. And we'll go ahead and do an example. We'll start that example in the second part of the presentation. And that will begin then on slide number 6. So the example will begin on presentation number 2.